The null hypothesis is that they're going to be equal to 0. The difference being 0, what does that mean? If the difference was 0, what does that mean as far as a mean difference?
Yeah, there is no difference.
There's absolutely no difference. That is your null hypothesis all the time. There's absolutely no difference. And so there can be, again, the standard tree, which is two-sided, right? One sided to the right or one sided to the left. D bar is the difference, the average difference, D bar. Why are we subtracting it from 0? Because that's the null hypothesis. Absolutely. Again, this is the same test statistic that we've dealt with the whole time. The exact same test statistic we dealt with the whole time. It's going to be a t-test. Why? Because chances are we don't know the mean, we don't know the standard deviation. So it's going to be a t-test. And again, we find the p-value same exact way as we always have. And we can do confidence intervals. Again, the same way we've always done. We may use the test to, we may use the confidence interval for a hypothesis test, in which case, if it's two-sided, it was not equal to. Again, the reason, so somebody raise their hand and tell me, why are we allowed to use the confidence interval as part of this test, the hypothesis testing, if it's two-sided, as opposed to if it's one-sided? Yes, Ebony. All right. Well, you're right around. You're kind of right around there.
What's the question?
Add to it, Michael. Right. Yes, exactly. So think about it like this, right? With a confidence interval, always two-sided.
Right, you're always two-sided.
Okay, with our confidence interval, you know, this is X bar.
Should it be D bar?
Yeah, you're right. Well, yeah, you're right. It should be D bar. Yes, in this case, right? And so if we're doing a 95% confidence interval, whatever the confidence interval is, right? The confidence interval is right here. This is alpha over 2. And alpha over 2. And so to get this T star for our confidence interval, right, it's going to be T star for our confidence interval is going to be the inverse T, 1 minus alpha over 2, common degrees of freedom. Always. The reason we can only use this when we're two-sided is because T star is only this if it's two-sided. If we're not two-sided, T star is going to be different. The T star that you get for your hypothesis test is different than the T star you use for the confidence interval when it's one-sided. Right? Because if it's not two-sided, we're not going to have alpha over 2. Does that make sense, everybody? Okay, that is the big kicker here. If it's not two-sided, this isn't alpha over 2.
It's just alpha.
It's just alpha.
That's
and
where
so the T star that we're going to use in our hypothesis test will be different in a one-sided null or alternative hypothesis than it is with a confidence interval. That's why we computed the confidence interval separately and didn't use it in the hypothesis test. We simply offered it as a potential candidate interval. Okay? We can calculate it, so we might as well calculate it and offer it because it gives us something to offer. Instead of just saying, nope, you're wrong, we're saying, nope, you're wrong, but here's something that we think is a legitimate boundary interval for the true population mean or the true population, the true difference or the true proportion, whatever it might be that we're working with. This is why we can only use a confidence interval in a hypothesis test if it's two-sided. Because the T stars will be different if it's one-sided. Any questions?
no, it's recorded.
Okay, so let's do some stuff here. All right. It is a claim that an industrial safety program is effective in reducing the loss of working hours due to a factory accident. The following data are collected concerning the weekly loss of working hours due to accidents in 6 plants both before and after the safety program is instituted. Okay, so So, the first thing we're going to do is what?
Put it in the one.
Well, I guess you can plug in the data.
Put in two,
Right.
yeah, you put
Okay,
two.
so we're going to say mu before, right, equals what? What is it? No, it doesn't equal mu after. Well, what does it mean, like in words?
Mu before is the proportion.
It mean what?
The mean population.
No, before. What does it mean before? What does it mean before?
Before the
what?
program.
Before the program was.
Before we took it, what about before the program?
The safety of the.
Yeah, but what are we measuring?
Working hours.
Right, we are, mu before is the average. The average hours lost due to factory accidents before the program. Okay, so you see here, if we don't know what mu before and mu after means, then there's no point in even doing this. Alright, we need to be specific. Absolutely positively specific in what these are. This is the, right, the average number of hours lost to factory accidents. Right. Before the program. And mu A is average number of hours after the program. Okay, it's so mu before minus mu after equals mu difference. And so if mu difference is positive, what does that mean? If the difference is positive, what does that mean? Well, so in our problem, what does that mean? What does it mean that the hours before is bigger than the hours
That
after?
means
Yes. It means the program worked. Why? Because you reduced the number of hours you lost from factory accidents. Okay? So a positive difference means, right, the program reduced the number of hours lost due to factory accidents. Okay, so just because we know how to do it, right, and we're at the end of the day, the actual statistics we're going to do on this isn't going to be very difficult. But what they mean is going to be the whole kicker here, right? The whole kicker. And so mu difference being negative means that the program failed. Well, the program added hours. Well, I mean, it doesn't mean it doesn't mean it added. Okay, it means okay. So let's be careful here. Okay,
Reduce the amount of
it
hours
doesn't
lost.
necessarily mean the program reduced the number of hours. Okay, so this is where we got to be careful in not explaining it, not reading too much into it. A mu difference means just the number of hours. Okay. We would like to attribute it to the program. But at the end of the day, right, we got to be careful. The difference is just the fact that before the program, there were more hours lost than after the program. Okay? More hours lost before the program than after.
Wait, so D positive, is that talking about the before?
Yes. Well, no, yeah. Well, I mean, you tell me, right? In order for mu D to be positive, before has to be bigger than after. Okay, so there were more hours lost before the program than after the program.
So what you're doing is just.
I'm just defining what these mean, so we know ahead of time. Because remember, in the weight loss deal, it was a good thing that the weight loss was positive. It was a good thing, right? So we've just got to be careful that we know what it is that we're getting out of these things.
Wait, so So if the mu d is greater than mu before.
Right? So think about it here. The hours lost before is bigger than the hours lost after. This is going to be a positive number because you got a big number subtracting a little number. If the hours after is bigger than the hours before, it's going to be negative because you got a small number being subtracted by a big number.
Unless there's no difference.
Well, then they'd be the same, yeah.
Yeah.
You know, and then they wouldn't be positive or negative; it'd be zero, right?
And then still the study wouldn't work, or the program wouldn't work.
More hours lost after than before. Okay, so again, this is very important aspect of doing the difference. We have to know what it is that we mean. We have to know what all this means. Okay, now that we do that, now, right, we're flat out coming in here and saying mu difference equals 0. And in this case, what do we want to study? We're interested in analyzing the differences which were computed as before minus after. In particular, assess if there has been a significant reduction in the loss of hours. Okay, so state the hypothesis and perform a test using a 10% significant level. Show all the steps. So now we're starting to get into questions that it's not going to tell you do this, then do this, then do this, then do this. It's going to tell you here's the scenario. Our alpha is 10%. Go to town. Okay, go to town. And it's our job to include everything that we need to include. All right, so here, what is our alternative hypothesis? A significant reduction. What would it mean for there to be a significant reduction?
That it would be positive, yeah.
Right, mu d is going to be what? And how do we say that using inequalities of zeros? Yes, greater than 0. Any questions on that? Okay, now do you see why it's such a big deal to determine what our difference means? What mu difference being positive and mu difference being negative means, because that's going to set our direction of extreme. And we know ahead of time what direction of extreme is a big deal. Okay, so now we can go in and we can enter all this stuff into our calculator. I can't see it. Okay, so clear everything out. Remember, we got to go into a list, into our data, enter it in. And again, they already did the differences, so just do the differences. There's no sense in reinventing the wheel unless you think they're wrong.
They're wrong.
They're wrong.
Okay, so there's 6 of them. And again, right, you might as well just do the difference. There's no sense in entering these in. They did it out for us. Okay, so now here, what are we going to do? What kind of a test are we going to do? Right, a t-test. We're going to do a paired t-test. We're going to do a paired t-test. Yes.
Remember yesterday, or not yesterday, last week you were saying, so doing t-test, it has to be smaller than 30?
Yeah, so remember, we don't know the population standard deviation, and we don't know n is less than or equal to 30. But we said, even if n is greater than or equal to 30, and we don't know the population standard deviation, it's still better off to do a t-test. So what I want,
Means versus proportions?
what's that?
So we're talking about means versus proportions?
Yes, the mean versus proportion. Means are probably going to be a t-test. Why? Because with a mean, you don't automatically know the standard deviation. With a proportion, it's always going to be a z-test because if we have some null hypothesis proportion, we automatically know the standard deviation. Right? Because the standard deviation is the square root of p times q over n. Where with the mean, just because you know the mean, we don't know what the standard deviation is. So here's the big rule of thumb, not just a little rule of thumb. This is the rule of thumb. If you're doing means, you're doing a t-test. If you're doing proportions, you're doing a z-test, period. Unless, by some freak chance, you know the exact population standard deviation, which is almost never given. Almost never. So that's the rule of thumb. That's the rule of thumb. So now, do you see, now we can do a t-test on this data. We can do a t-test on this data. We can go into stats, over to test, down to 2, do a t-test, and are we going to do data or stat? Data. And so our mu naught is what? 0. List 1, frequency, and are we going to be greater than 0 or less than 0? Greater than, bam.
Do you enter the data already?
Greater than mu naught.
Okay, is there any questions? You see what I'm talking about? We didn't do hardly any computations. But if we don't know what a computation means, then we're toast.
Where's the calculator?
Okay, I just moved it up.
Yeah, okay, got that. Yep.
Okay, so here's all of the information that we need. All of it. And what else should we do? Since we're here. Okay, yeah, we should do T-star. What else?
We should test,
Yeah, T interval. Bam. Test T interval.
oh, just to offer it. Oh, I see.
And we're going to do data over 1. And what is our confidence level? 0.90, because it's at a 10% alpha. Boom. Bam. Okay. Are we going to use our T interval? Are we going to use our confidence interval in our hypothesis test?
No.
Why not?
Not double-sided.
Right, it's not two-sided. This is one-sided. Okay, so you see what we're doing? We're just getting all of our ducks in a row here. And you're right. We should do T interval. We have to get our T-star, which again is distribution down to inverse T.
What confidence level did you get?
And again, remember, what was I going to say? Oh yeah, if you have a TI-83 and don't have inverse T, it took Bradley all about 10 minutes total to download this program.
It's super, that video is super easy.
Yeah, and that's why we offer it, because it's about as straightforward as you can get. Yes.
Someone willing to offer me to borrow their cord?
I don't have a cord, but
I have one.
The YouTube
I
video
can
is
bring it.
super easy. Like, she explains it, and like.
oh yeah, you don't need a cord. You're gonna program it into your calculator following this video. Or if somebody has a cord, it can take 2 seconds. Yeah. It can literally take 2 seconds if somebody has a cord. Okay.
If you haven't
The
done it,
video
by
is super quick.
Just remember, after you download the video, when you go and hit program interval T, you gotta hit enter before it starts. You can't. Here, we hit enter and it's ready to take it. You have to hit enter again, and it just takes it asks you verbatim for this type of stuff. Okay, so our T interval, so 0.9. How come we're using 0.9?
Because it's 10%
Right, and
levels.
how come we didn't do 1 minus alpha over 2?
Because it's not two-sided.
It's not two-sided. It's only one-sided, right? So we know that all of our 10% is on one side. So we go up to 0.9 and we're golden. Does that make sense? So for here, for T-star, this is 0. Our T-star is here. This is alpha equals 10%. All right, because it's only one-sided. It's one-sided, and so it's not broken up into 2. It's only 1 minus alpha over 2 if it's two-sided. If it's one-sided, it's 1 minus alpha. Okay, or just alpha if we were looking at the other side, right? If we were looking down below, if this happened to be mu difference was less than 0, then we would be down here, and T-star would be alpha. Right? Remember, with the T-stars and the Z-stars, you got to take it into context. Okay. And comma what?
5.
5, right? Because our n was 6. So n minus 1 is 5. Bam, we got our inverse T and our T-star. Okay, so we did all kinds of stuff here, right? We did all kinds of stuff. All right,
Yeah.
so
That's true.
okay, so our T observed,
I got a different one.
our T observed is about equal to 1.464. Our p-value is about equal to what?
1016.
Yeah, 102. Okay, our T star is about equal to 1.476.
So it's pretty dang close to our.
And our interval is pretty close, yeah.
Goals.
So if the T star is, or the T observed is greater than the T star, that means it's in the
Why?
rejection region.
Why? In this case, why?
Because
Right, because our direction of extreme was to the right. So in order to be in the rejection region, we had to be farther right than T star. If our direction of extreme was to the left, it would be less than, because farther to the left would mean extreme. Okay? So, does that make sense?
yes.
Okay, so now, yeah, we're not extreme. Notice, all kinds of things are working together. Even though we cannot offer this as a hypothesis test, should it surprise us that it contains 0?
No,
Why not?
because 0 is the mean.
Okay, well, it's a mean difference, remember, we're talking about a difference. Why should we not be surprised, even though we're not going to use it? We can't use the confidence interval in the hypothesis test because it wasn't two-sided.
Oh, because
But
Because
we're not
It's
terribly
standard error.
surprised that it contains 0. Why?
90% of the intervals will be.
Well, yeah, but what does it mean? So, what would it mean that a confidence interval contains 0? Yeah, so this says if we repeat, the confidence interval is, if we do this test, if we collect sample after sample and after sample, right? 90% of the confidence intervals we build will contain the true population proportion, or difference. And in this case, it contains 0, which is saying that the true difference is 0. How is that backed up by the data? What is our
because it is
p
not.
value?
Yeah, it's not more than one standard.
Right, our p-value is not less than or equal to alpha.
Yeah.
And our t observed is not greater than or equal to our t
Yeah.
star. So all of these lead us to fail to reject the null. And failing to reject the null means that we failed to say that there's enough evidence to suggest that this is wrong, which means our data is not statistically significant, and we have to assume that the true population, or the true difference is 0.
Okay.
Okay, so all of that together. Okay, so T observed was less than T star. Our p-value was greater than alpha, just barely, right? Therefore, we fail to reject the null. This means we do not have enough evidence to suggest mu d is different from 0. Our 90% confidence interval also contains 0. Which, although not used in the test, suggests is a reasonable conclusion. Alright, and so on and so forth, right? This is where you put on your poet hat and you just, make the magic words flow from the pen. Okay? And convince everybody that you're right. Okay, any questions? Are you getting what we're doing now? This is statistics. This is all we ever do is statistics, basically. We're going to do it different ways. We're going to be in different types of distribution. Here, the distribution was, here the data set was a set of differences, but we did the exact same thing. We listed a null hypothesis. We listed an alternative hypothesis. The null hypothesis provided us with the distribution. The alternative hypothesis, so the null hypothesis provided us with a distribution, the alternative provided us with a direction of extreme, and then we just went and tested it. We tested it by finding a test statistic and a cutoff value for standard deviation for the cutoff, or for a cutoff for the standard deviation extreme, and we got a p-value and we compared it to alpha. And for good measure, we constructed a confidence interval. And that's what we're doing every single time. Every single time, no matter what it is that we are going to do, that is what we do. No matter what kind of data we have or what kind of distributions we're going to be in, that is what we do every single time. All of it. All the time. That's it. That's it. Right there. And notice, there wasn't a whole lot of calculation involved. Heck, we didn't even do any calculations, really. Other than, I guess, T-star. Right? Other than T-star, I suppose, we did this calculation. But other than that, we threw stuff into the calculator or a computer and got numbers out. It's all about the interpretation of the numbers. And so, notice, a good chunk of our work was done before we ever entered a single piece of information into the calculator. Right? Because we had to know what it was that our numbers meant after we got them out. If we don't know what they mean, then it's completely worthless.
So we're going to be explaining that all before we get to
Oh, yes.
Okay.
Yes,
I need to know that. That's fine.
Any questions?
For the sake of satisfying curiosity.
Absolutely.
Is there ever a situation where your results are legit, but like the relationship between T-odds and T-star tells you one thing, and P-value tells you another?
No, because they're both calculated from the exact same data.
Okay.
They're really, these are just two different ways of saying the same thing. They're really just two different ways of saying the exact same thing.
Okay, that's what I thought.
But one of them, see, I shouldn't say they're two different ways of saying the same thing. They're two different concepts explaining the same result. Okay? With the p-value, you're talking about the probability of collecting data and observing our statistic in anything more extreme, assuming that the null hypothesis is true. So we're testing the null by going and collecting data and finding the probability that if the null is true, what's the probability that we randomly selected this data and got these results? Okay? The T observed and the T star, okay, that's also built on the data, but what we're doing is instead of having a probability of getting our data, we're looking at how many standard deviations our data set was away from the number of standard deviations that are confident or that are alpha value level of significance deemed extreme. So although they're kind of reinforcing one another, they're using two different concepts and two different ideas to explain the result. Yeah, to explain the result. So they're not the same thing. I shouldn't say they're the same thing. They're completely different, really. One of them's a probability of getting a result. One of them's actually, this is the number of standard deviations away from the mean. Okay. Let's look at this example. A company advertises that food preparation time can be significantly reduced with a mega slicer. A random sample of 12 people present at the local food prep conference prepared the ingredients for a meal with and without the slicer. For each person, the order in which the measurements were obtained were also randomized, i.e. flip a coin, heads, right, then do without first, otherwise do with first. Wow.
What?
Okay, so that's what it says. You can read it. They just flipped a coin. Okay, they flipped a coin, and whether or not they used the slicer first, and then did it without the slicer, or they did it without the slicer first, and then with the slicer. That's all. Okay, so to help avoid any bias that may arise due to a learning effect over time. Okay, so basically, if I'm sitting there watching you do something, I might see that you do it this way, and I might, skew the result. Okay, but anyway, suppose that the difference between the preparation times with minus or without minus with follows a normal density. Okay, which test should be used?
T-test.
Why? Well, of course a t-test, but what kind? Do we have any reason to pair these together?
Yes.
Yes, absolutely we have reason to pair them together because basically we're assuming that the same person doing it with the slicer and without the slicer. What's that? Well, so this isn't a two sample here. In this case, okay, so the reason we're not in a two sample yet is because, yes, we do have two samples, but what we're doing the statistics on is a single sample of the differences. Okay, so that's an excellent point. Don't confuse. So with a paired t-test, with a paired situation, with a paired situation, what we're really doing is the same stuff. We're just creating a different data set. And it's a data set of differences. Okay, so here it's paired. Absolutely. It's going to be a paired t-test. And why is it going to be a t-test? Right, we don't have a standard deviation. And our samples are tiny. We only have 12 of them. Okay, so give the appropriate null alternative hypothesis for this. Okay, so the B here, what is our null always? Okay, so what would be the company's claim? Well, again, we've got to do a little bit of work first before we can make this out. So mu width equals mean prep time with slicer, and mu without equals
So it's different foods. It's weird without the B and A. I don't know which one would go first.
well, without and with, I don't know. It's not always going to be before and after. It's without and with in this case. Prep time without. Okay, so here they want us to do what? They want us to do without minus with, right? So without.
So tell us.
So we're going to use the difference data set.
Okay, so a positive means what?
Okay, positive.
Yes. A positive, yes, right, means it's longer without. Right? A positive means it took longer without the slicer. So a mu positive means longer time, longer prep time without slicer. And a negative means less prep time with slicer. No. Yes, so means longer prep time with slicer. Okay. And so again, this might seem obvious, but it's only obvious until you don't write this stuff down. Once you don't write it down, then you become all screwed up and everything gets jumbled up in your head. Just take the 5 seconds, or not even 5. Take the minute to write this down. It forces you to ask these questions. Okay, 40, and this is gonna be critical when we go in and write up our final results. Is there any question?
I'm just kind of trying to figure
All
out.
right, so if the without is larger than the with, if the time without is bigger than the with, then the difference is going to be positive.
I was
Okay,
just
so
trying
that
to
means it took longer without the slice. If the mean time, if the width is bigger, then we're going to get a negative number, which means it took more time with the slice. So what do we want to see if we're the company? Do we want to see a positive difference or a negative difference? We want to see a positive difference. Why?
Because we wanted to increase
Yeah,
speed.
we want to show that we had less time with, or more. It took more time without the slice there, so that people buy the slices. Okay, and now we're right back. Okay, so and what is the alternative?
That it's less than greater than, or yeah.
What?
What is the claim? That it can be reduced, right?
Yeah, it can be reduced.
So which one do we want?
No greater than.
Right. We want mu d to be greater than 0. We want the difference to be positive. Why? Because that would mean that the mean longer prep time without slicer. Wow. So longer prep time without the slicer, as opposed to longer prep with the slicer. Right? Any questions? Okay. So now we just go in and we enter in our data.
Let's see.
Just go in, we enter in our data. That's 2, 7, negative 2. 2, 7, negative 2, 8, 0.
-3, -4, -6, 5, and 3. Wow.
That -6 needs to get out of there.
Yeah, there's
Oh, right, it's a 6.
no, it's not 6. It's not.
Yeah, negative
Yeah,
3,
there.
negative 4, 6, 5, and 2. All right. And so at this point, it's pretty much cake, right? So, again, the homework and the exam shouldn't really scare you because it's all about how much time you're going to put into the little details and then writing it up.
That's
Right? It's not scary at all.
Just
I always like when I can bullshit because I tend to bullshit pretty good. I mean, really, like if just writing out your explanation, that's easy. So stat, test, t-test, with data, pretty much everything stays the same,
Say
right?
good to beauty, yeah.
It's the same.
Yeah.
Now list 2.
Boom. So we threw this out there. And then we're going to go in and we're going to go to 8, which is a t interval. We're going to do data. But we're going to do what?
What's the level?
I think
95.
it's a 5% significance level this time. Yeah. 5% significance. No. So keep in mind, alpha being 5% and a 95% confidence
It's
interval are one and the same.
2.5, it's 9.75.
Okay, it's one and the same. Well, but yeah, we don't even need it. We don't. It doesn't even matter. Calculator take care of that.
If it was,
Right? Remember, we don't care about the 1 minus alpha over 2 because the confidence interval is created by the calculator. You're going to have to create a confidence interval by hand, at which point you're going to have to care about the alpha over 2. But when we throw it in here, the calculator knows it. Right? The calculator knows it.
that's
I
where I
always
was
wanna
confused.
do it.
That's where I was getting confused earlier.
What's that?
Uh,
What else do we need to do? Oh, yeah, we need to find our t-star.
inverse.
Right? So we go to second distribution down to 4.
Oh, that's when you do 0.9.
No. We're not doing alpha over 2. We're doing 0.95.
11.
The T star, that was for the T star that you had on the
Right.
board.
That was for the confidence interval. This T-star, again, remember, The only time they're ever the same is when it's two-sided. If it's not two-sided, they should not be the same. They should not be the same. Okay? And remember, we don't have to worry about the confidence interval T star if we're doing T interval because it takes care of it for us. Okay. Right? And so here, this is going to be 0.95 because remember, it's one-sided. So all 5% of the alpha is in the same direction. Okay? Ask yourself that question. When you're going to define your T star, ask yourself, alpha over 2 or not alpha over 2? If all of alpha has to be in one direction, regardless of whether it's above it or below it, it's not going to be alpha over 2. Alpha over 2 is when alpha's in two directions, and it's split up. Okay, and then, comma, what did we, 11? And that's it? Okay. Right, just this. This is T star, and that's about equal to 1.796. And again, the last problem was a good example of why we should probably go to at least 3 decimal points. Right? Had we rounded everything, we might have been equal. P-value might have been equal to alpha, and we might have rejected, or we might have rejected, where technically we probably shouldn't have. And then of course, right, our T observed is about equal to 1.409. Right, and we're going to fail to reject again. P-value is 0.093, and again, so it all rejected. And remember, again, when we got our interval, we shouldn't have been that terribly surprised that we were going to reject, even though we can't use this in the test. It shouldn't surprise us that it contains 0. Okay? It should not surprise us that it contains 0. 95% confidence interval. And again, somebody explain in words what this confidence interval means.
Why are we rejecting it if our T is...
Oh, we're not.
Yeah, okay.
Somebody explain to me what this 95% confidence interval means. Elena, is that a hand up?
Yeah, I'll answer it, and then I have a question afterwards. That 95% confidence interval means that if you repeated the same process, you get a bunch of different confidence intervals, and 95% of them contain the true population.
Perfect. And the true population difference. Yes, perfect. And then your question.
Would the difference between in the last problem, how it was so close, you said if we didn't even round it, we may have.
Right.
You know, would that indicate would that be any indication of maybe the amount of effectiveness?
So the effect size, so I think what you're talking about is this thing, the effect size. I have not really talked about effect size a whole lot.
Okay.
But there is this thing called effect size, and it's very, very similar to a test statistic. And basically, it's kind of to compare two different samples. Okay, so the effect size is like two different samples if you wanted to compare. Okay, but I haven't gotten necessarily into effect size because I think that that's something that is better handled in a class where scope is a little beyond this one. Okay, but it's not necessarily about the effectiveness of the treatment. It's basically because they're so close. That would be where maybe you might want to do some more tests. Or remember we said that p-value less than or equal to alpha means you reject. And then we're like, except if they're actually equal, you might not really want to reject because you're right on the cusp of your significance level. That's an example of that, where, okay, well, yeah, I mean technically we can reject, but we're, yeah. Generally, when you do statistics and you really want something good, you're looking for a tiny p-value.
Okay.
Okay. Any questions? Okay, so. Yeah. Now instead of pairing things up, we just have two samples. Okay? And this is where people tend to freak out. Oh my God, look at a bunch of variables. And oh my God, look at a bunch of crazy equations. And holy smokes, look at all of this craziness. It's not that bad. Okay? We're not ever going to I'm not going to ever make you do this stuff by hand.
Ever?
I should. It's not that tough. I should make you do one of them by hand just so you can go and see. Look at. Notice.
We have it on video.
No. Wait just a second. Wait just a second. What's N1?
Sample 1.
Yes. What's N2?
Sample 2.
Okay. What is S of 1?
Standard deviation 1.
Yeah. What's S of 2?
Sample standard deviation 2.
Okay. Then you got everything you need to know. You just plug it in, right? You just plug it into a calculator.
So we still
That's
don't
it.
want to do it?
Okay, that's it. That's all that is. Okay, as scary as this look, all you're doing is plugging some things into a calculator that you already got from a calculator.
But then,
Yeah.
when you plug things into the calculator, sometimes, for some reason, it didn't come out right.
Right, it's because you were lacking on the correct order of operations in your calculator, which is why we hammered you so heavily in Math 120, and you learned to hate all math professors because of 120. Okay, because we were so hard on you about correct order of operations. If you don't know correct order of operations, then computers are completely lost to you, except checking Facebook. All right, let's take a quick break.
What's SP's standard deviation?
Pooled standard deviation.
We will